I've noticed formal charges. Lewis dot structure in general do not represent the actual shape of the molecule in case of polyatomic ions. The net charge is possessed by the ions as a whole and not by a particular atom. It is, however, feasible to assign a formal charge on each atom. The formal charge of an atom in a polyatomic molecule or ion may be defined as the difference between the number of valence electrons of that atom in an isolated or free state and the number of electrons assigned to that atom in the Lewis structure is expressed as. So what this means to say that formal charge, it is the net charge on on a particular atom, right? It is a net charge on a particular atom which can be calculated by total number of valence electron present in the electron in the free atom minus total number of non-bonding lone pair electrons. Means we have to check if there is a lone pair, and if there is a lone pair, then how many lone pair are there. So lone pair into 2, you will get the total number of electrons minus half of total number of bonding electrons shared, right? How half of number of like bond electrons are there. Like if I will give you an example like C H H, right? So this part can be calculated by minus half, or like you can just consider half divided by 4. 4 because one electron here, one electron here, one electron here, one electron here. Those are the shared electrons, right? So you will get the bonding electrons of carbon, like 2, right? Now, the counting is based on the assumption of that the atom in the molecule owns one electron of each shared pair, both the electrons of a lone pair. Let us consider the ozone molecule O3. The Lewis structure O3 may be drawn. So O3 can be drawn like this. You can practice by you can do it before seeing this. You can try to calculate formal charge, right? This is the way how you can calculate. If you want to you can mark 1 2 3. If you want to calculate for one, like see how many valence electron oxygen has, 6, minus how many electrons it has in the lone pair, 2, right? So minus 2 minus half of bonded electrons, so 1 2 3 4 5 6, and half of that, right? So like this, in this way you can get the answer, right? So similarly for all, hence we represent O3 with formal charge R as follows. So O3 can be represented like this, including this formal charge, which is very important, right? So what this means is that whenever oxygen is forming 3 bond, then it becomes plus. When only 1 bond, then it becomes minus. When 2 bonds, it becomes zero charge, right? We must understand that formal charge does not indicate the real charge separation within the molecule. Indicating the charges on the atom in the Lewis structure only helps in keeping track of the valence electron in the molecule. Formal charges help in the selection of the lowest energy structure from uh, from a number of possible Lewis structures for a given species. Generally, the lowest energy structure is one with the smallest formal charges on the atoms. The formal charge is a factor based on a pure covalent view of bonding in which electron pairs are shared equally by neighboring atoms. Now what this means is that generally generally what happens, the lowest energy structure means the structure which has lowest energy is with one with the smallest formal charge on the atoms. Now, what this means to say that if the bond has structure is with low energy, then the formal charge on the atoms will also be low. Of course, that is true. The formal charge is a factor based on pure covalent view of bonding in which electron pairs are shared equally by neighboring atoms. Right. Now, let us come over here. Limitations of octet rule. The octet rule, though useful, is not universal. It is quite useful for understanding the structures of most of the organic compound and it applies mainly to the second period of the elements of the table. There are three types of exceptions to the octet rule. The incomplete octet of the central atom. In some compounds, the number of atoms surrounding the central atom is less than 8. This is especially the case with the element having less than 4 valence electrons. Example: LiCl, BeH2, VCl3, right? So these are the electrons they do, even though they don't have octet in their octet configuration, but then also they form bond and they become stable. Now, odd electron molecules. In molecule with odd number of electron like nitric oxide NO and nitrogen oxide NO2, the octet rule is not satisfied for all the atoms, right? Like in this case of NO, like how many electron does nitrogen has? 4, 5, 6, 7. Right? 7. It is less than 8. How many oxygen have? 1, 2, 3, 4. Oxygen is satisfied, but nitrogen is not satisfied. Right? So what means to say that whenever like nitrogen has 5 valence electron, right? 5. So since odd number of electron molecules, they don't get sometimes stability. It's not compulsory all the time. Sometimes, right? The expanded octet, the elements in and beyond the third period of the periodic table apart from 3s and 3p orbitals, 3d orbitals also available for bonding. In a number of compounds of these elements, there are more than 8 valence electrons around the central atoms. This is termed as expanded octet. Obviously, octet rule does not apply in such cases. So now what this means to say is that whenever he in this case it was lacking of octet, like it was having 7 electrons, but in expanded octet it has more than 8 electrons, right? More than octet electrons. So they are also one point to note here is that these expanded octet are also known as hypervalent, right? They are also known as hypervalent down or super octet. This is important. Super, okay, super octet. Better to the, it's not looking good. Right? Yeah. So let us go forward. This termed as expanded octet. Obviously, the octet rule does not apply in such cases. So if you take the example of PF5, SF6, H2SO4, the number of coordinate compounds. So now see this case, PF5. How many electron does phosphorus has? 1, 2, 3, 4, 5, 5 into 2, 10 electrons. So 10 electrons means it is more than it. So that has expanded up, right? Similarly for H2SO4, this H2SO4 figure, this Lewis figure is very important. It comes many times in exam, right? Let us go forward. Interestingly, sulfur also forms many compounds in which octet rule is obeyed. In sulfur dichloride, the sulfur atom has an octet of electrons around it. Look, so now interestingly, sulfur also forms many compound which the octet rule is obeyed. In sulfur dichloride, so means sulfur is generally known for not obeying octet rule, right? But in this case, it is obeying, like as sulfur chloride, right? SCl2. 1, 2, 3, 4, 5, 6, 7, 8, 8 electrons. So therefore it is following octet rule, right? So now other drawbacks of octet theory. It is clear that octet rule is based upon the chemical inertness of noble gases. However, some noble gases, for example xenon, krypton, also combine with oxygen and fluorine to form a number of compounds like uh, XeF2, KrF2, XeOF2, etc. This theory does not account for the shape of the molecule. So what this theory does not give the shape of the molecule, it does not explain the relative stability or the molecule being totally silent about the energy of the molecule. Means it does not give stability, means energy, we cannot predict the energy of the compound because we know that energy is inversely proportional to stability. So since we can't predict the energy, we cannot predict even the stability, right? and this theory does not even allow us to imagine how the shape of the compound would be. So that was these drawbacks were the reason why other theories came. So we will study them in the next lecture, right? Bye guys, take care. This will be covered in lecture 4. I'll see you guys in lecture 4. Bye.